Alright, welcome to Physics 390's podcast for Maxwell's Equations. We're going to sum up everything we've learned and try to make sure we can describe all electric and magnetic field interactions. So to get started, I've got Maxwell's Equations for what we understand up to this point today. We've got Gauss's law right here. And basically Gauss's law tells us that if we enclose a certain amount of charge, this electric field has to penetrate through some surface. Then we have Faraday's law here, which tells us if we go around a closed loop, the change in potential around that loop has to be zero. And then we have Gauss's law for magnetic field, or no magnetic monopoles. This tells us that if you enclose a magnetic dipole on north and south pole, you get no magnetic flux going through your closed surface. And then the last one is Amperes Law. This tells us that if you enclose a certain amount of charge in a certain amount of current in an Amperian loop, conventional current in an Amperian loop, you will be able to determine its magnetic field. Well, what did Maxwell's do to get all these four equations named after him? Well, in about the 1830s, Maxwell noticed a problem with what we usually refer to as Faraday's law. If you integrate around a closed loop, and he corrected it to look like this, what we presently call Faraday's law with Maxwell's corrections. The question is, how did he correct it? He corrected it using this method. So we know this, and what he used was Stokes Theorem to help verify his ideas. Well, what is Stokes Theorem? Stokes Theorem's claim, if you have a curl of a vector and take the dot product with dA and integrate over that area, that is equivalent to writing out the closed line integral around the outer boundaries of this area, dot dl, and we know that as an EMF. Now, what else do we know about EMFs? Well, we learned if we have a rate of change of magnetic flux, a negative rate of change of magnetic flux, that also produces EMF. Well, what is magnetic flux? We define magnetic flux as the integral of B dot dA across over some area, or the magnetic field punches through this particular area. If we take the curl of E part and set it equal to the rate of change in time of the magnetic flux, we have this relationship. Now, this looks different, but what I'm going to do is, it doesn't matter which order you take the derivative or integral. So what I'm going to suggest is we change that order. And I'm going to move the differentiation inside the integral along with the minus sign. Now, when I do that, what happens? Well, we get these two integrals. And now if you look at the integral itself, these integrals are the same. I have on the left and the right-hand side an area integral that is dotted into dA. Now that means if the integrals are equal, the left-hand side equals the right-hand side, then what's inside also has to be equal. So this is how we validated that this version of Faraday's law is correct. What did he do next? So we call this the differential form of Faraday's law. And that minus sign there, this little thing right here, that comes from Lenz's law. And if you remember the earlier podcast, Lenz's law induces a B field that resists the change in magnetic flux, and that B field is created by a current. And then you can figure out, and that current usually goes the opposite of the current in any other direction. All right, so there is another correction. Maxwell also found another problem with Amperes Law. Now here's what he said about Amperes Law. What he did is take the divergence of that whole equation. So you get the divergence of the right and left-hand sides here. And the big question is, does this have to equal 0? In the past, in magnetostatics, we've said the divergence of J equals 0. So if we use that, the left-hand side would also equal 0. But earlier we showed that the divergence of J is equal to the negative rate of change of the charge density. So which one is correct? And then this also is known as charge conservation. So since it's a conservation law, we better stick with being correct. So what did Maxwell do? Well, you've got this divergence, and in magnetostatics, it's equal to 0 because there's no rate of change of charge density. But in general, the right-hand side of this, the divergence of the current density, is not equal to 0. So we have to somehow compensate for this inconsistency. And the other problem is, if you take the divergence of the curl of anything, the mathematical identity says it's 0. So we've got to deal with these inconsistencies to make sure that the right-hand side equals the left-hand side. And so Maxwell did this great intuitive thinking. He took the charge conservation rule right here and Gauss's law that we knew are correct. And then he took Gauss's law and solved it for the charge density. And well, there's my charge density. Well, he plugged it back into the conservation of charge idea, and we get this relationship. Again, we have a derivative here in time and a derivative here in space. And again, it doesn't matter. And then epsilon naught is constant. It shouldn't matter if you take one derivative before the other. So the way we take the derivative shouldn't matter. So what I'm going to do is change the position of the time derivative and the position derivatives and write it in this manner. So if I write it in this manner, what I can do is now it looks like I might have divergence on each side. And so what we can say is I'll factor out that divergence, and I get that the current density is equivalent to this term over here, minus epsilon naught, the partial derivative of the electric field with respect to time. And what that tells us is we've got this current density here that we haven't been dealing with before, and this was Maxwell's great insight, is we were just dealing with the a charge density, and we were dealing with a charge density that was created by a B field, or the charge density that created the B field. We were not looking at any rate of changes of electric field that could also create a charge density. Well, this charge density is usually called by a special name, and it's displacement current, or displacement current density. So Maxwell realized that Ampere's law is off by this negative term here, and to compensate for that, so he found out that the right-hand side was not, he found out that the right-hand side here is not correct. We're missing a term here. We're off by this negative value with this displacement current. And so to compensate for that, what Maxwell did was add that term. He also multiplied, since it's a current which is multiplied by epsilon naught, you have to include that epsilon naught. So if we add this term to this side, then everything is consistent. When you take the divergence of both sides, they should be zero. The math is consistent. And this is usually referred to as Maxwell's correction to Amperes law. And we get Amperes law to deal for any case. You have a current that can create the B field. You can also have a changing electric field in time that can also create a B field. This kind of linked all the laws together into this representation. You've got Gauss's law here. So you got Gauss's law that didn't change. You got no magnetic monopoles that didn't change. But now you've got the full version of Faraday's law that a changing B field can create an electric field. Changing B field in time can create an electric field. You notice that these derivatives are not total derivatives, they're partial derivatives, because the B field can also be a function of position along with time. So we have to deal with that. You've got the full version of Ampere's law with Maxwell's corrections. And again, there's a partial derivative with respect to the E field, and that's again because the E field can change in time but also change in space. So we have to deal with that eventuality. And then you have the force equation of what we call the Lorentz force equation. And from these 5 equations, you can describe everything that goes on with Maxwell's equation. So I hope you enjoyed the second podcast in Physics 390, and I hope to see you soon.